So I'm going to talk about gamma, the Lorentz factor, which we have already done a video about, but there's enough to say about it that I thought we'd do a kind of gamma reloaded video and have another go at it.
Gamma reloaded,
Yeah.
I like that. Nice.
Gamma is a factor that comes up in special relativity. It's kind of appears in a lot of the equations in special relativity, and one of the places it occurs in this thing is this thing called time dilation. You see something going past you, so something that's traveling relative to you, the clocks in that reference frame seem to be going slow relative to your reference frame, so the time, the clocks tick more slowly and everything goes more slowly. Biological processes go more slowly, radioactive decay goes more slowly, and so on. So really, time really is slowed down when something's moving relative to you. Okay, so in our last video about this, we talked about one of the proofs that this actually occurs, which is that there are these particles called muons created when high energy particles crash into the top of the atmosphere, and the muons are then detected down on the Earth. And the reason why this is a bit of a surprise is because muons don't live very long, they have very short decay times. And actually, if you just figure it out, even traveling at the speed of light, the fastest light speed they could travel at, the muons don't actually have enough time to make it to the Earth. So most of the muons should have decayed before they get to the Earth. But actually, if you put a muon detector on the Earth, you find plenty of them are getting through. And the reason is because these muons are traveling at high speeds close to the speed of light. That means that, as measured from our reference frame, their clocks are going more slowly, which means that they don't decay so quickly, and so they have actually got time to get all the way down to the Earth without decaying. As measured in our reference frame, suddenly their lifetimes become maybe 10 or 100 times longer than they were. And the factor by which they become longer is actually this factor, this gamma factor that we're talking about. So as I say, there is lots of other phenomena that are sort of associated with this factor of gamma, and one that we can get at quite easily is by thinking about what happens from the muon's point of view. Right, so from a muon's point of view, it comes into existence, it's suddenly born somewhere at the top of the atmosphere, and it sees the Earth rushing up to meet it. Okay, so it's just sitting there and sees the Earth coming towards it, because that's, that's relativity, that's what it's all about. And the question is, well, in its own reference frame, it's just going to live as long as it usually does, right? There's nothing special going on as far as this muon's concerned, it's just sitting there stationary, and so actually, if it looks at its watch, everything's, times are going at the normal kind of rate. And so it's going to live for the normal lifetime that a muon's going to live for. And so in its reference frame, if it had the same distance to travel, it wouldn't live long enough. The Earth rushing up towards it there wouldn't be time for the Earth to travel out 50 or 100 kilometers from where it was when it was first created to smash into it. And so there's got to be some other effect that's going on that, from the muon's perspective, actually allows it to reach the Earth, because it does reach the Earth. We can detect them on the Earth, and so the muon has to also agree that it reaches the Earth. And so this other factor is this thing called Lorentz contraction, that as well as time being affected by motion, distances are affected by motion as well. And so when something's moving along the line of sight in the direction it's moving, distances get squashed. So instead of it having to travel 50 kilometers from being created down to the Earth, it might only have to travel a few hundred meters, because in its reference frame it sees that distance greatly compressed. And so all the distances are squashed in that direction. So as far as it's concerned, the Earth's atmosphere is only about 50 meters thick, and it only has to travel that 50 meters, so it actually has time to get all the way from the top of the atmosphere to the Earth. Because even though its clock's going at the normal kind of speed, it sees all the distances squashed. And remember, it's actually only contracted in the direction that the muon's moving. So actually everything gets really distorted. So your tree has the normal width, but is suddenly a few millimeters high maybe. So actually, things look very, very weird from your perspective when you're traveling close to the speed of light, because all these distances get contracted. But there's a famous thought experiment involving a train and a tunnel. The idea is you've got a train and you've got a tunnel which is exactly the same length as the train. And so if you're a train spotter who's standing there beside the railway watching the trains go by, you see this train approaching, and because this train's moving relative to you, you see it Lorentz contracted. It's a bit shorter than it should be. And that means that as it goes into the tunnel, it disappears completely in the tunnel, right? Because it's shorter than the tunnel. Like, the tunnel's not moving relative to you, you're standing next to it, so therefore the tunnel is its normal length. But because this train is moving relative to you, it becomes a little bit shorter, so it disappears into the tunnel. Fine, so it actually is briefly kind of hidden at both ends of the tunnel. But now if we think about somebody sitting on the train's perspective, somebody sitting on the train, they think they're stationary, the table there in front of them, they can drink their cup of coffee, when they put it down it just stays there, so they're in their reference frame and everything's normal, and they're seeing the countryside rushing by, and so they see this tunnel approaching them at high speed, and of course because they're seeing this tunnel moving, the tunnel should be contracted. And so from their perspective, they should never completely disappear into the tunnel, because they see a tunnel which is shorter than the train, so therefore the train never completely disappears. By the time the back end of the train's disappeared into the tunnel, the front end's come out the other end. Right? And that's all well and good, and okay, maybe they just agree to differ about whether the train is shorter than the tunnel or not. But unfortunately, you can then do another experiment, which is you can say, okay, so if this train spotter actually is, has a lot of power, and bizarrely someone has installed two large guillotines, one at either end of the tunnel, And at the moment the train disappears into the tunnel, he pulls a lever which briefly makes these guillotines come down and then go back up again. Then from his perspective, that's fine because the train's disappeared into the tunnel. He can do that without doing any damage. Okay? From the point of view of somebody approaching the tunnel, if this happens, it's not going to be such good news because from their perspective, the train's longer than the tunnel, which means either the front of the train gets chopped off or the back of the train gets chopped off or both. Okay? And this is something that everyone has to agree on, right? Because if you actually do the experiment, either you end up with a smashed train or you don't. And ultimately, that's going to be something that everyone has to agree about. It's not something that you can just say, well, that's just a matter of perspective. That's all just relative, right? Either the train gets broken or it doesn't.
So what happens?
So there is a resolution to this paradox, and the resolution to this paradox turns out to be something very fundamental in relativity, and it's called the relativity of simultaneity, which basically means which things which are simultaneous in one reference frame are not necessarily simultaneous in another reference frame. So in fact, both of these people agree that the train doesn't get smashed, but the reason why they agree the train doesn't get smashed is different, right? The guy who's pulling the lever says, well, the train obviously didn't get smashed because it was shorter than the tunnel, so that was fine. The guy in the train sees something completely different in that what he says is that actually what happened is the train was approaching. Before it went right through the tunnel, the front guillotine came down and went back up again. Then after it had pretty much passed through, the back guillotine came down and back up again. And so actually they kind of missed the train as it went through. And so this is what both of them see. They both agree that actually the train's fine, but the reason is that because the things which were simultaneous in one reference frame, the guy who was just standing next to the tunnel said these things happened both at the same time. The guy who's in the train said actually no, one happened first, then the other. And so that's the resolution to the paradox, is that this whole concept of simultaneity kind of goes away in special relativity. That things which one person says both these things happened at the same time, somebody else will say no, actually that one happened first and that one happened second. Because whether things happen at the same time really depends on what reference frame you're measuring them in.
But what's the fact? Did the train disappear in the tunnel or did it fall out the ends? What actually happened?
Both. It just depends on whose reference frame you're in, right? In one reference frame, that's exactly what happens. If you think about it, the train sticking out at both ends of the tunnel relies on somebody's simultaneous measurements, right? The front was sticking out at the same time that the back was sticking out. And because different people disagree about simultaneity, it's quite possible for them to disagree about whether both ends of the train are sticking out of the tunnel at the same time.
How does this go down when you teach this to students?
The students love it, I have to say. One of the really nice things is, although we avoid all the maths in these videos, actually the maths you need to do this properly isn't very hard. The most difficult maths you need to do this properly is trigonometry and just basically Pythagoras' theorem. The square on the hypotenuse is equal to the sum of the squares on the other two sides. So the nice thing about it is this is something which is actually mathematically not that difficult, but which is conceptually mind-blowing. And so it's actually one of the things we teach the students quite early. It's in the first semester of the first year here. Just because it's something where you can do the maths, but actually end up with a result that has you really scratching your head. And actually one of the things I always warn the students when we're starting to do this is that usually in physics, what we tell them repeatedly is if you get something that looks like a stupid answer at the end, you've probably done something wrong. So go back, check, make sure you haven't messed up. This is one of those cases where if you get something that looks like a stupid answer at the end, you've probably done it right, because the results that come out of special relativity are so bizarre that actually you do end up with these apparent paradoxes all over the place.